All right, welcome back to the deep dive. Today we're diving into something I think is pretty fundamental to how our universe works, really, at all scales, from galaxies to, atoms.
Yeah, I mean, it's all about spinning, right?
Yeah.
The rotation of rigid bodies.
Yeah, and I think we sort of take this for granted in a lot of ways. It just kind of happens.
Right.
But when you really start to think about it, it's kind of amazing that everything's spinning.
Yeah, and it's not just planets and stars. I mean, think about everyday things too, like the wheels on a car or a CD spinning in a player.
Right, a Blu-ray disc or an airplane propeller.
Yeah,
All of these things rely on the principles of rotational motion.
exactly. And that's what we're going to unpack in this deep dive.
Yeah.
We have a really comprehensive chapter here that introduces all the core concepts of rigid body rotation.
For our listener, we want to make sure that this deep dive is structured and clear and insightful. We're going to extract the key knowledge from the source material, making it accessible and interesting without overwhelming you with equations.
Right. We'll highlight the essential theories and concepts, delve into some real-world applications, and hopefully leave you with a solid grasp of how things spin and why it matters.
So to kick things off, let's tackle the first big idea. How do we even describe rotation in a rigorous way?
Well, we need a way to measure, first and foremost, the angle of rotation.
The angular position, right. It's sort of like the rotational equivalent of just, a regular position in space.
Precisely. And that's where this idea of an angular coordinate comes in. Our source uses the Greek letter theta to represent this, and it basically tells you how much something has rotated from a starting point. Like imagine the hand of a clock.
Oh, I see. So if the hand starts at, say, 12 o'clock and then moves to 3 o'clock, that's a rotation of 90 degrees.
Right. And we can think of that starting position, that 12 o'clock mark, as our fixed axis, like the positive x-axis, for example. The angular coordinate, then, is the angle between that fixed axis and the reference line on the rotating object, in this case, the clock hand.
Okay, so it's not just about the amount of rotation, but also about, having reference point and defining a direction.
That's crucial. We have to be clear about which way we consider positive rotation. Typically, counterclockwise is the standard, but you could absolutely choose clockwise if you wanted.
As long as you're consistent, right?
Yeah.
Like if you pick clockwise as positive, then a rotation from 12 o'clock to 3 o'clock would be negative 90 degrees.
Exactly. It's all about setting up a clear frame of reference. So now that we can talk about angular position, we need to describe how quickly something is rotating. And that's where angular velocity comes in.
This is sort of like how fast something is moving in a linear sense, but for rotations, it's how fast the angle is changing.
Exactly. The angular velocity, often represented as omega z, tells us the rate of change of that angular coordinate over time. So it might be, how many degrees or radians per second the object is spinning.
Radians. Why radians instead of degrees?
That's a great question. Radians are just a more natural unit for measuring angles when you're dealing with rotation, especially when we start connecting rotational motion to linear motion, as we'll see later.
Got it. So we have this angular velocity, and it can be positive or negative depending on whether the rotation is counterclockwise or clockwise, based on our chosen convention.
Exactly. And we can talk about average angular velocity over a period of time, which is simply the total angular displacement divided by the time taken.
Okay, and the units would be radians per second, or maybe revolutions per second, or revolutions per minute, RPM.
Right. It's important to be able to convert between those different units. Remember that one full revolution all the way around a circle is equal to 2 pi 2 radians.
Now, here's a really interesting point that the source makes. If you have a rigid body that's rotating, like let's say a vinyl record spinning on a turntable,
Okay, yeah.
every single point on that record, whether it's near the center or at the edge, has the same angular velocity.
That's absolutely right. They're all locked together, moving through the same angle in the same amount of time.
Intuitively, it kind of makes sense. Now, just like things moving in a straight line can speed up or slow down, a rotating object can also change its angular velocity.
Right, and we have a term for that. Angular acceleration, often shown as alpha delta-Q. It's the rate of change of the angular velocity, so how much the angular velocity is increasing or decreasing per unit of time.
So if something's spinning faster and faster, it has a positive angular acceleration. If it's slowing down, it's negative angular acceleration, sort of like deceleration.
Precisely. The average angular acceleration is the change in angular velocity divided by the time interval, and the units are radians per second squared.
Makes sense. It's like the rotational analog of linear acceleration, which we're probably more familiar with.
Right. Now, there's a really important concept that the source brings up here. It's this idea that angular velocity and angular acceleration are actually vector quantities. Yeah, which means they have both a magnitude, how fast it's rotating or how quickly the rotation is changing, and a direction.
That makes sense for linear motion. But how can rotation have a direction? It's just spinning.
Well, for the type of rotation we're mainly focusing on in this chapter, rotation around a fixed axis, the direction of the angular velocity and acceleration vectors is actually along that axis of rotation.
So, for example, if something is spinning counterclockwise around the z-axis, the angular velocity vector points up along the positive z-axis.
Exactly. And if it were spinning clockwise, the vector would point down along the negative z-axis.
Ah, okay, I see. But it's a little counterintuitive, right? The motion is circular, but the vector describing that motion is actually perpendicular to that circle along the axis of rotation.
Yeah, it is a bit tricky to wrap your head around at first. And the source actually highlights this in a caution box because it's a common misunderstanding.
People might think that the angular velocity vector is sort of like tangent to the circle, pointing in the direction of the motion at a given point.
Right, but that's not the case. The angular velocity vector is a property of the entire rigid body, and it's always along that axis of rotation. And this becomes even more important when you start dealing with situations where the axis of rotation itself is changing. But for now, we're sticking with fixed axis rotation, which simplifies things.
Okay, that makes sense. To solidify these concepts, the source dives into a really practical example involving a flywheel. What can we glean from that?
So in example 9.1, we're given a specific mathematical function that describes the angular position of the flywheel as it changes over time. And the cool thing is, by using calculus, we can actually find the instantaneous angular velocity at any given moment.
Calculus, that sounds a little intimidating.
Don't worry, you don't have to solve the equations yourself. The source walks you through it step by step. The main takeaway is that you can figure out how fast the flywheel is rotating at any particular instant, even if its angular speed is constantly changing.
Oh, so we're not just limited to average angular velocity over a time interval.
No, we can actually pinpoint the exact angular velocity at a specific time. And that's really powerful because it lets you analyze how the rotational motion is evolving in a more detailed way.
Got it. Now, let's say we have a situation where the angular acceleration is constant. That seems like a simpler scenario, but probably still pretty useful to understand.
Absolutely. Just like with linear motion, having a constant acceleration makes things much easier to analyze. And the source points out that there's a whole set of kinematic equations for rotational motion with constant angular acceleration that are strikingly similar to the ones we use for linear motion.
Really? So if I remember my physics equations from way back when,
Yeah.
we had things like distance equals velocity times time plus 1/2 acceleration times time squared.
Right, and it turns out there's a rotational equivalent of that equation. Theta equals theta naught plus omega naughts times time t plus 1/2 alphas in time squared.
So it's like we just swap out the linear variables for their angular counterparts. Distance becomes angular displacement, velocity becomes angular velocity, and so on.
Exactly. And there are three other key equations that follow this same pattern, which are all summarized in table 9.1 in the source material. It's a really helpful table to have on hand if you're working through problems involving rotation.
So this is like our toolbox for analyzing rotational motion when the angular acceleration is constant.
Precisely. It lets us solve for things like final angular velocity, angular displacement, time, and even the initial angular velocity, given certain other known quantities.
Just like we did with linear motion. But it's really important to emphasize, as the source does, that these equations only apply when the angular acceleration is constant.
Right, it's a very specific scenario. If the angular acceleration is changing, then these equations won't give you the correct answer.
Okay, fair enough. And the source actually gives a nice example of how to use these equations in action with a spinning disk that's gradually slowing down.
Yes, example 9.3. We have a disk that starts off spinning at a certain rate, and then a braking force is applied, creating a constant negative angular acceleration.
So it's like when you hit the brakes on your car, but instead of linear deceleration, it's angular deceleration.
Exactly. And the example walks us through how to use the kinematic equations to calculate the final angular velocity after a given time, and the total angular displacement, how many radians or revolutions the disk spins through as it comes to a stop.
Really helpful to see those equations being put to use in a composite example.
Uh,
Now, so far, we've been describing the rotation itself, but what about the actual movement of points on the rotating object?
that's where things get really interesting, because now we start to connect the rotational motion to linear motion. If you think about a point on the rim of a spinning wheel.
Yeah, it's obviously moving in a circle. It has a linear speed and probably a linear acceleration as well, even if the wheel is spinning at a constant rate.
Exactly right. So every point on a rotating rigid body is moving in a circular path. And the source gives us a really elegant equation that relates the angular displacement, theta, to the actual distance traveled by that point along its circular arc, which we call the arc length ACE.
And that equation is,
E's equals r times theta, where r is the distance of the point from the axis of rotation, basically, the radius of the circle it's moving in.
so if you know the angle of rotation in radians and the radius of the circle, you can instantly calculate how far the point has traveled along that circular path.
And it's super important to remember that theta has to be in radians for this equation to work.
Right, because radians are kind of like the natural unit for measuring angles in rotational motion. It's like they directly connect the angular world to the linear world.
Exactly. Degrees just wouldn't work in that equation. Now, we can also relate the angular speed omega to the linear speed of the point.
And that's just the regular speed we're used to, right? Like miles per hour or meters per second.
Right. The equation is v equals r times omega. V equals r. So the linear speed of a point on a rotating object is directly proportional to both its distance from the axis of rotation and the angular speed of the rotation.
That makes intuitive sense. If you have a merry-go-round, the horses on the outer edge are moving much faster than the ones closer to the center, even though they're all rotating at the same angular speed.
Precisely. The outer horses have to cover a much larger distance in the same amount of time to keep up with the rotation. Now, what about acceleration? Because as you pointed out, even if the wheel is spinning at a constant rate, the points on the rim are constantly changing direction, which means they must be experiencing some acceleration.
Right, because acceleration is any change in velocity, either in its magnitude, speeding up or slowing down, or in its direction.
Exactly. So for a point moving in a circle, we can break down its linear acceleration into two components: tangential acceleration, atan, and radial acceleration, arad, which is often called centripetal acceleration.
Tangential and radial. I remember those terms from circular motion.
Tangential acceleration acts along the tangent to the circle at the point's location, and it's responsible for changing the magnitude of the linear velocity. So if the point is speeding up or slowing down along its circular path, that's due to tangential acceleration.
And it's related to the angular acceleration.
Absolutely. The equation is atan equals r times alpha. Atan equals alpha. So the tangential acceleration of a point is equal to the radius of the circle times the angular acceleration. And there's a sign convention here that the source highlights. If alpha is positive, atan is also positive, meaning the point is speeding up along its path. If alpha is negative, atan is negative, meaning the point is slowing down.
Okay, that makes sense. What about radial acceleration? That's the one that's always pointing towards the center of the circle, right? Keeping the object moving in that circular path.
Exactly. Radial acceleration, arad, is always directed inward, towards the center of the circle. And it's responsible for the continuous change in the direction of the linear velocity, even if the point is moving at a constant speed.
I remember the equation for that. Rad equals v squared divided by r. R equals v vor. So the faster the point is moving and the smaller the radius of the circle, the greater the radial acceleration.
That's right. And you can also express arad in terms of angular speed. Arad equals r times omega squared. Arad equals r.
So even if the angular speed is constant, there's still a radial acceleration that's keeping the point moving in a circle.
Precisely. And the source provides a really helpful example here to illustrate these concepts. A discus thrower. In example 9.4, we're given the angular speed and angular acceleration of the discus as the athlete is spinning.
So not only is the discus spinning, but it's also spinning faster and faster.
Right, and the example shows us how to calculate both the tangential and radial acceleration of a point on the rim of the discus. Because it has both an angular speed and an angular acceleration, it experiences both types of linear acceleration.
So to find the total linear acceleration, we'd have to combine those two components, right?
Exactly. And because they're perpendicular to each other, tangential along the path, radial towards the center, we can use the Pythagorean theorem to find the magnitude of the total acceleration. It's a classic vector addition problem.
I love how the source ties these concepts to real-world scenarios. It makes them much more concrete and easier to grasp. And it's not just the discus thrower, right? They also talk about Blu-ray discs and airplane propellers.
Those are fantastic examples. With the Blu-ray disc, the challenge is to read data off the disc at a constant linear speed. But as the laser reading head moves outwards from the center, the radius is increasing.
So to maintain that constant linear speed, the angular speed of the disk actually has to decrease.
That's right. It's a direct consequence of the V equals R times omega VR equation. As R increases, omega has to decrease to keep V constant.
That's really clever. It's like the disk is spinning slower and slower as the laser reads further out.
Precisely. And the airplane propeller example is even more complex because the tip of the propeller has a speed that's a combination of its rotational speed and the forward speed of the plane.
So it's like a vector addition problem again.
Right. And engineers have to carefully consider this when designing propellers because if the tip speed gets too high, exceeding the speed of sound, for example, it can create a lot of noise and reduce the efficiency of the propeller.
Okay, we've covered a lot of ground here, from describing rotation to relating it to linear motion. Now, let's shift gears a bit and talk about the energy involved when something is rotating.
It's clear that a rotating object has kinetic energy, right? I mean, think about a spinning flywheel. It can do work, so it must possess energy.
But how do we calculate that energy? It's not just the regular 1/2 mv squared equation, is it?
No, because not all parts of the rotating object are moving at the same speed. Points further from the axis of rotation are moving faster.
So how do we account for that?
Well, the source takes us through a really nice derivation. It starts by considering the kinetic energy of each individual particle that makes up the rotating object. Each particle has a mass, m, and a speed, v.
And we know the kinetic energy of a single particle is 1/2 m times v squared.
Exactly. So the total kinetic energy of the rotating object is the sum of the kinetic energies of all those particles. But we can simplify this using the relationship between linear speed and angular speed. V equals r times omega, v rho.
Where r is the distance of that particle from the axis of rotation.
Right. So when we substitute that into the expression for the total kinetic energy, we end up with a term that looks like 1/2 omega squared, multiplied by the sum of m times r squared for all the particles.
And that sum of m times r squared is what we call the moment of inertia, denoted by the letter I.
You got it. And the moment of inertia is a really fundamental concept in rotational motion. It essentially captures how the mass of the object is distributed relative to the axis of rotation.
So it's not just about the total mass, but also about how that mass is spread out.
Exactly. A heavier object might have a smaller moment of inertia than a lighter object if its mass is concentrated closer to the axis of rotation.
I see. So the moment of inertia tells us how resistant the object is to changes in its rotational motion. It's kind of like the rotational equivalent of mass in linear motion.
That's a great analogy. Just like a larger mass requires more force to accelerate it, a larger moment of inertia requires more torque, which we'll talk about in the next chapter, to change its angular velocity.
So it's harder to get a spinning object with a large moment of inertia to speed up or slow down.
Precisely. And the units for moment of inertia are kilogram meter squared. A much. Now, one common mistake that the source warns against is assuming that all the mass of an object is concentrated at its center of mass when calculating the moment of inertia.
Yeah, I can see how that would be tempting, but it wouldn't be accurate in most cases.
Right. And they provide a good example to illustrate this point, example 9.6, which involves a machine part made up of 3 disks.
So by changing the axis of rotation, you get a different moment of inertia, even though the object itself is the same.
Exactly. The distribution of mass relative to the axis is what matters. Now that we have this concept of moment of inertia, we can write the equation for rotational kinetic energy in a compact form. K equals 1/2 I times omega squared. K equals I sum V.
So it's beautifully analogous to the equation for linear kinetic energy. 1/2 enough times z squared. Mass is replaced by moment of inertia, and linear speed is replaced by angular speed.
Exactly. And this allows us to analyze the energy of rotating systems using the same principles of energy conservation that we've already learned.
Right. The total mechanical energy of the system, which can now include rotational kinetic energy, translational kinetic energy, and potential energy, remains constant if there are no non-conservative forces like friction doing work.
Precisely. The source gives some great examples of this with problems involving an unwinding cable attached to a rotating object, like a cylinder or a drum.
So in those examples, as the object falls, it loses potential energy, which gets converted into both translational kinetic energy of the falling object and rotational kinetic energy of the spinning object.
Right, and we can use the equation v equals r times omega, v equal r, to connect the linear speed of the falling object to the angular speed of the rotating object.
Where r is the radius of the rotating object. And then we can use energy conservation to solve for things like the final angular speed of the rotating object or the speed of the falling mass.
Absolutely. It's a powerful technique for analyzing these types of problems.
And when we're dealing with the gravitational potential energy of a rotating object, we can treat it as if all its mass is concentrated at its center of mass, right?
That's right. The equation for the gravitational potential energy of an expended object is U equals mu sess, U equal m in U sess, where m is the total mass, g is the acceleration due to gravity, and nu sum is the height of the center of mass above some reference level.
Okay, so we can use that to calculate changes in potential energy as the object rotates and its center of mass changes height.
Exactly. It simplifies the calculations quite a bit. Now, I know we've thrown a lot of equations and concepts at our listener today, and you might be wondering, how do we actually calculate the moment of inertia for different shapes?
Yeah, it seems like it could get pretty complicated, especially for objects with complex shapes.
It can. But luckily, there's a really useful theorem that can simplify things in many cases. The parallel axis theorem.
Tell me more about that.
So this theorem says that if you know the moment of inertia of an object about an axis that passes through its center of mass, you can easily calculate the moment of inertia about any other axis that's parallel to that one.
Okay, that sounds really useful. What's the equation?
It's IP equals I2 plus MD squared. IP plus IP plus MD squared, where IP is the moment of inertia about the parallel axis, IP is the moment of inertia about the axis through the center of mass, M is the total mass of the object, and D is the distance between the two parallel axes.
So if you shift the axis of rotation, you just add this extra term m squared to the original moment of inertia.
Precisely. And what's interesting is that this theorem implies that an object has its minimum moment of inertia about an axis that passes through its center of mass.
That makes sense because if you think about it, rotating something about an axis that's off-center is going to require more effort.
Right. And the source even points out that, for this reason, rotation about an object's center of mass often feels like the most natural or the easiest to initiate. It has the least resistance to changes in rotational motion.
Okay, that's a really cool insight. And the source actually gives an example of how to use this parallel axis theorem in reverse to find ICMM if you know IP and Z.
Yes, example 9.9. It's a good illustration of how powerful this theorem can be. And the test your understanding section includes another nice example involving a pool cue, which shows how the mass distribution and the parallel axis theorem affect the moment of inertia about different points of rotation.
Okay, so we have a tool for finding the moment of inertia about parallel axis. But what about calculating it from scratch for continuous objects, like a solid cylinder or a sphere?
That's where we need to bring in the power of calculus. Instead of summing over discrete masses, we have to integrate over the entire mass distribution of the object.
Sounds a bit more challenging.
It can be, but the source walks us through it step by step. The general formula for the moment of inertia of a continuous object is I equals the integral of r squared dm, IR dm.
Where dm is a tiny element of mass, and r is its distance from the axis of rotation.
Right. And if the object has a uniform density, we can express dm as par times dv, where dv is a tiny element of volume.
So the integral becomes I equals ρ times the integral of r squared dv.
Exactly. And the trickiest part is usually choosing the right volume element, dv, so that all parts of that element are at roughly the same distance from the axis of rotation.
I can see how that would get a little tricky for complex shapes.
It definitely can. But the source provides us with worked-out examples for a hollow cylinder and a uniform sphere, which are really helpful to study.
So in example 9.10, they calculate the moment of inertia of a hollow cylinder rotating about its central axis. And they end up with the formula I equals 1/2 m times the quantity r1 squared plus r2 squared, where r1 and r2 are the inner and outer radii of the cylinder.
Right. And what's cool is that if you set r1 to 0, you get the formula for a solid cylinder. And if you make r1 very close to r2, you get the formula for a thin-walled cylinder. And these all match the results summarized in Table 9.2, which is a really handy reference for the moments of inertia of various common shapes.
So we don't have to go through the integration process every time. We can just look up the formula in the table.
In most cases, yes.
Yeah.
And example 9.1 tackles the more challenging case of a uniform solid sphere rotating about an axis through its center.
And they use a clever technique of integrating over thin disks to find the moment of inertia, which turns out to be two fixed mr squared, where m is the mass and r is the radius.
Exactly. And the source points out that this is actually smaller than the moment of inertia of a solid cylinder with the same mass and radius.
That's because more of the sphere's mass is concentrated closer to the axis of rotation, right?
Exactly. The distribution of mass really matters.
Well, I think we've covered a tremendous amount of material in this deep dive into the rotation of rigid bodies.
Yeah, we really have. We started by defining the basic quantities of angular position, velocity, and acceleration. And we saw how closely they parallel the concepts we use for linear motion.
Right. Then we explored the special case of constant angular acceleration, and we derived those really useful kinematic equations that allow us to solve problems just like we did for linear motion.
And then we delved into the connection between rotational motion and the linear motion of points on the rotating object.
Right. Those equations relating angular displacement to arc length and angular speed to linear speed are really fundamental. And then we introduced the concept of rotational kinetic energy and the all-important moment of inertia. Yeah, the moment of inertia is such a crucial concept. We saw how it depends not just on the mass, but also on the distribution of that mass relative to the axis of rotation.
Absolutely. And we talked about the parallel axis theorem, which is a really handy tool for calculating a moment of inertia about different axes.
And finally, we touched on the more advanced techniques of calculus that we need to use to find the moment of inertia for continuous objects.
It's been a whirlwind tour of rotational motion, but I think we've hit on all the key concepts.
We definitely have. And for our listener, I hope we've provided some real aha moments along the way.
I hope so too. It's fascinating to see how so many of the principles we've learned about linear motion have direct analogs in rotational motion.
It really highlights the elegance and interconnectedness of physics. Now, as our listener goes about their day, what's a thought-provoking question we can leave them with, something to ponder about rotational motion?
I would say take a moment to look around you and think about all the rotating objects you encounter. From the wheels on cars and bicycles to the blades of fans and the gears in machines.
And even things like the Earth spinning on its axis.
Exactly, and consider how the distribution of mass in each of those objects influences its rotational behavior. Why do some things spin so easily, while others require a lot of effort to get going?
And what other physical quantities that we typically think of in a linear context might also have meaningful rotational counterparts?
Those are great questions to ponder. And for those who are feeling inspired to explore further, there's a whole world of applications of these principles in engineering, sports, astronomy, and countless other fields.
Right, the principles of rotational motion are truly fundamental to understanding how our universe works at all scales.
They are indeed. And in our next deep dive, we'll build on this foundation by introducing the concept of torque and exploring how it causes changes in rotational motion.
So we'll finally get to answer the question of why things start spinning or stop spinning.
Exactly. That will give us a more complete picture of the dynamics of rotation.
Fantastic. Well, thanks for joining us on this deep dive into the rotation of rigid bodies. Until next time.
Thanks for having me.
Always a pleasure.
See you next time.
All right, bye.
Bye.